Hello everybody, my name is Khalid Hussein. I'm PhD student at Faculty of Engineering and Environment, Northumbria University, Newcastle, United Kingdom. I'm going to present my research with the title Performance Evaluation for a 10 kilowatt solar organic Rankine cycle power system to operate in the UK climate conditions. So, the outlines of this presentation: motivation, background about the solar energy organic Rankine cycle, problem statement, the aim of this study, the solar organic Rankine cycle system under consideration, methodology, working fluid selection, mathematical model, organic Rankine cycle parameters and operating conditions, results, and finally conclusion. Motivation. When we talk about the energy, we should talk about the environment as well, because the energy directly affect the environment, our environment. So energy is an essential commodity in human life. It plays a crucial role in economic development of the nations and in society overall well-being. Where does this energy mainly come from? 80% of the worldwide energy use in 2008 is based on fossil fuels. The energy demand is affected by the following factors: population, economic growth, and per capita energy consumption. It's expected that in 2050 the energy demand will be doubled. Also, for a fixed amount of fossil fuel, increasing these factors will lead to the fuel depletion and increasing the negative impacts on the environment. So, this is the main drivers behind to shift to alternative cleaner energy sources. One of these clean sources is solar energy. Solar energy is by far the largest and depleted energy source. How big solar energy is? This is a very interesting figure which compares the annual world energy consumption in 2009 with all renewable and non-renewable energy sources. The yellow ball here represents the annual amount of solar energy which can be collected on the Earth's surface. This is the wind, ocean, biomass, etc. These poles represent the fixed amount of conventional fuel, including fossil and nuclear. If we compare the annual amount of solar energy with the other conventional fossil and nuclear, we will find solar energy is larger than 10 times. If we compare the solar energy with other renewable energy, including wind, ocean, biomass, we will find solar energy is about 250 times. If we compare solar energy with the energy consumption, world energy consumption during the 2009, we will find that solar energy is about 1500 times. So, as we have seen, the solar energy is a huge source of energy. However, the geographic location plays a main role in what kind of solar system can be implemented. For high temperature solar plants, the solar belt between 40 degrees north and south is ideally preferred. Outside this belt, less potential of using conventional high temperature solar plants due to low temperature limitation and large collectors area required. Organic Rankine cycle technology can be used even in the places with relatively low solar radiance due to its characteristics to efficiently recover low-grade sources. Organic Rankine cycle is basically similar to conventional Rankine cycle, which is a thermodynamic cycle converting thermal energy to mechanical energy. The main difference is using organic fluids instead of water. These fluids have low boiling points, which allow exploiting energy from low temperature heat sources, such as solar, geothermal, biomass, or waste heat from industrial processes. How does an organic Rankine cycle look like? This figure shows a typical 1 megawatt organic Rankine cycle unit from turbine. It consists of four main parts or components. So this is the evaporator, turbine, pump, and condenser. These are small scale organic Rankine cycle units including all main components with a capacity of 10 kilowatt from two different providers. It can be seen the dimensions in meters on both units showing how small they are. Such sizes don't need a big problem statement. Because solar energy is considered as a low temperature heat source, it is a challenging task to use it to run a conventional Rankine cycle with high temperature, especially in the locations characterized with low solar radiation. So using organic Rankine cycle technology with low boiling temperature fluids is a promising solution for power generation with utilization of the aim of the study. The aim of this research is to develop a reliable model for a small-scale solar organic Rankine cycle power system with a capacity of 10 kilowatt in order to evaluate and predict its performance for the UK climate conditions. The required areas of the solar collector, evaporator and condenser together with the mass flow rate of the working fluid are determined for two different organic fluids. This study will assist in designing and optimization of a 10 kilowatt solar biomass organic Rankine cycle power plant to be erected at Northumbria University. The solar organic Rankine cycle system under consideration for this study is illustrated in this figure, schematically in this figure, with its TS diagram. It consists mainly of two circuits: the solar collector circuit with heat transfer fluid and the organic fluid circuit. The organic Rankine circuit consists of the evaporator, expander, condenser, and the working fluid pump. For the solar circuit, it consists of a field of evacuated tube solar collector which used to heat up the heat transfer fluid which passed through the evaporator. The working fluid is heated by passing or heat exchange from the heat transfer fluid to the working fluid. The heated working fluid passes through the expander to generate mechanical work which is converted after that to electricity using the generator. The organic fluid passing or exit from the expander passes through the condenser, which heat is rejected to the cooling water, condensing the working fluid to liquid state. The liquid organic fluid is pumped to high pressure to point 2 with high pressure and heated up again, and the cycle repeats each other. Methodology. The methodology starts with the selection of the appropriate working fluid, then building the mathematical model of the whole system components, developing the model of the solar organic Rankine cycle system using Thermolib toolbox, which works under MATLAB Simulink environment to solve the mathematical model, then applying the operating condition which contains the location and season and organic Rankine cycle parameters to predict the system performance. Working fluid selection. There is a wide range of organic fluid candidates for organic Rankine cycle systems. Numerous studies reported that the working fluid plays a vital role in the organic Rankine cycle system performance, and therefore the working fluid should be carefully selected to achieve the highest possible system performance. Although many studies have focused on the selection of most appropriate ones, no single fluid has been identified as ultimately optimal for all organic Rankine cycles. In this study, the working fluid are selected depending on the temperature level of the heat source and based on literature. R134A and 2 and R245FA are the most used with low temperature heat sources less than 150 degrees Celsius. And these two working fluids are selected for this study. The thermophysical properties of the working fluids are shown in this table. As we can see, the most important point that both fluids have zero ozone depletion potential. The mathematical model. The solar evacuated tube solar collector efficiency can be determined from the following equation. As a function of the solar radiation, collector mean temperature between inlet and outlet, and ambient temperature. A1, A0, A1 and A2 are constant provided by the solar collector manufacturer. To evaluate the organic Rankine cycle system, two parameters are calculated: the overall system efficiency and the organic Rankine cycle efficiency. Both are determined from the following relations, where the net power output is calculated as introduced in this equation, and the heat added to the organic Rankine cycle is determined from this relation. To evaluate and determine each part of the heat exchanger area for the evaporator and the condenser, the long mean temperature difference method is used. The working fluid properties are calculated using the built-in thermodynamic function, which is built in Thermolib toolbox. Organic Rankine cycle parameters and operating conditions. The location that has been selected for this study is Newcastle upon Tyne city. It lies in the north of England, in this place as shown in this map. The season selected is summer. The global solar radiance used in this study is 700 watt per square meter. The maximum evaporation pressure is limited to 30 bar. The maximum cycle temperature is 100 degrees Celsius. The condensation temperature is set to be 30 degrees Celsius, and the ambient temperature is 25. The expander and pump efficiency used in this study are 70 and 80% respectively. The Thermolib model developed. As mentioned earlier, Thermolib toolbox is used to simulate the solar organic Rankine cycle power system, which works under MATLAB environment. Thermolib has a friendly user interface. As can be seen, the Thermolib model shows the components in the form of blocks. Each block represents a component in the real cycle. For example, this is the condenser, this liquid tank to collect the condensed fluid, and this is the pump, solar collector, and the turbine. Under each block, all the related equations and parameters are implemented. For example, if we see what's under the expander, what's under this component expander, we can see all the equations, related equations that use it to calculate the performance of the turbine and the power output, everything. Under this block, we can see this is what under this block, all the equations and parameters related to this component. Results. At the beginning, the results were obtained at the same evacuated tube solar collector area, 180 square meter. We can see from the first figure the net output power against evaporation pressure. We can see that the net output power for R245FA is much higher than R134A. Also, we can see that this fluid R245 requires lower evaporation pressure, which means that lower safety aspects for the evaporation in all the components of the cycle. This figure shows the both organic Rankine cycle efficiency and the system efficiency for the two fluids. We can see from this figure that R245FA has higher efficiencies, organic Rankine cycle efficiency and system efficiency than the R134A. Because the temperature, the maximum cycle temperature, 100 degrees Celsius of R134A is not reached, so superheating this fluid after evaporation is needed to reach the 100 degrees Celsius. So these two figures shows the effect of the expander inlet temperature after superheating for R134A. The first figure shows the net output power against the expander inlet temperature. We can see that the net power output increases with the increase of the expander inlet temperature. On the other hand, both organic Rankine cycle efficiency and system efficiency increase with the increase of expander inlet temperature. So better performance has been obtained with the increase of the expander inlet temperature. After conducting the sensitivity analysis to see the effect of different parameters on the system performance for the two working fluids, the comprehensive calculation results for the two fluids are obtained at their optimal system performance to make a comparison between these two fluids to produce 10 kilowatt gross output. So we can see that R245FA requires less power consumption from the pump, and this maybe affect the net output power, which means that more net output power for the R245FA. The evaporation pressure for R245FA is less, so less safety consideration for the system components. Both the organic Rankine cycle efficiency and system efficiency are higher for R245FA. The working fluid mass flow rate is 0.393, which is less for the refrigerant 245FA, and this is the reason why the pump work is less. The other results related to the solar collector area and the different components of the heat exchanger areas. So we can see that R245FA requires less solar collector area and of course less cost. The total heat exchanger area for R245FA is less as well, with 72, and that for the R134A is 83 square meter. Also, For the expander consideration, the expander outlet volume flow rate and the expander ratio outlet to inlet volume flow rate for the R134A is less, which means that less volume of the expander is required for R134A. So as a conclusion, the following points can be drawn from the performance of the system of two fluids. A better system performance was obtained using R245FA in terms of overall system efficiency and the net output power. The system with R245FA requires less areas of both evacuated tube cell collector and heat exchanger. In terms of the expander, R134A seems to have a smaller expander size. Finally, coupling solar energy to organic Rankine cycle is a promising application which could meet the sufficient power needs and mitigate the climate change. Thank you for your attention.